So let's start applying Newton's laws. Honestly and truly, what we're really doing is we're applying free body diagrams. So first, let's talk about elevators. Most elevators are suspended by a single cable. So if the elevator is at rest, then, oh no, I want to do it down here. The tension upward in the cable is exactly equal to the force of gravity downward, because the net force is 0. Now, if the net force is 0, that not only applies at rest, but it also applies to constant velocity. Now, in order to accelerate upward, we need a greater tension than the force of gravity. Oh, I need to move this down a little bit. So if my force of gravity is 2 notebook lines long, I need my upward acceleration to be bigger. If I want to accelerate downwards, again using force of gravity is 2, I need a shorter tension. So the tension is greater than the force of gravity here. The tension is less than the force of gravity here. How much greater and how much less? By the amount of the net force. So if you knew the acceleration, then to find this tension, you'd say force of gravity plus the net force gives me the tension. Or force of gravity minus the net force gives me the tension. If I told you the tension and you had the force of gravity, you could find the acceleration. It depends on which order you want to work. Now remember, accelerating upwards does not mean moving upwards. Accelerating upwards occurs if you are speeding up upwards or moving downwards and slowing down. Accelerating downwards happens if you're speeding up downwards or moving upwards and slowing down. The acceleration and velocity, if they're in the same direction, you have speeding up, opposite direction, slowing down. So you've got to know both pieces of information. Now, if we have a student inside an elevator, the free body diagram of the student is slightly different because the student is not touching the cable. The cable is on the outside of the elevator. So this would be the force of gravity of the student. These were all of the whole elevator. And this would be the normal force. Remember, that means the force from a surface, in this case, the floor. So when the elevator is at rest or moving at constant velocity, these two are equal and the student feels normal. When the elevator is accelerating upwards, this has to be bigger than this. The student feels heavier. The student's weight did not change. The normal force changed. When you're accelerating downwards, this is smaller than this. Again, the student didn't change weight. You feel lighter because the normal force is less. You never feel your own weight. You feel objects pushing against you, often because of your weight. So the normal force is what tells you how you feel you're moving. Also, a scale, a bathroom scale, it measures normal force. It does not measure your weight. Now, if you're at rest, so the normal force and your force of gravity are the same, then yes, the scale's measurement, the normal force, is equal to your weight. But, for instance, when you first step on the scale, the dial goes way higher and then it settles in the middle because the scale is both holding you up, supporting your weight, and it's stopping you. It's making you accelerate, your foot accelerate upwards. So that normal force is much greater than your actual weight. So now we're going to move on to ramps. Ramps, I'm pretty sure that's barely on the screen. Let's move it up. So if we have an object on a ramp, we virtually always measure the angle of the ramp from the horizontal. Okay. I'll usually say it in the problem, but the angle is always measured for the horizontal. So no friction yet in the class. So if we have an object on a ramp, force of gravity is still straight down. Gravity pulls straight down towards the center of the earth. Normal force is called normal force because normal means perpendicular to the surface. So on a ramp, the normal force is not drawn towards the top of the paper. It's drawn perpendicular to the surface, right here. Now this object is going to possibly accelerate down the ramp, slide at constant velocity down the ramp, accelerate up the ramp, slide at constant velocity up the ramp, or stay in place, depending on what other forces are involved. So we are going to accelerate along the surface. So in other situations, if we had something at an angle on the paper like this, like the normal force is now, we would break it up into x and y components. On ramps, we don't do that. And that is because we're going to accelerate along the surface. Imagine if we did do that. So then this box is sliding down, and so it's got an x component of acceleration and a y component of acceleration, and you have to put them back together. It's easier to turn our coordinate system. So we're going to have on ramps, this is x and this is y, and x can point either direction. Because realize, whoever originally defined that our coordinate plane, that positive x is to the right and positive y is up, they didn't have to do it that way. They could have said this was positive x. They could have said this was positive y. Of course, they could have named this m and n, or q and r. They chose x and they chose to the right to be positive. They chose y, they chose up to be positive. So we're making a different choice. For ramps, along the surface is x, perpendicular to the surface is y. So we don't need to break up the normal force. We need to break up the force of gravity. So if I redraw this, just like we did with all those equilibrium problems yesterday, we have FGY and FGX. And most of the time on these problems, the normal force is going to be exactly equal to FGY. If it wasn't, the object would crash down through the ramp or fly up into the air. Then the x component is along the surface of the ramp, so that causes this object to accelerate downward. Or it resists. If there's a rope here pulling up, this resists the upward pull, but it's this part that resists it, not the full gravity. The y component and the normal force cancel each other out. So now let's talk about the trig functions. If I make a bigger triangle, that's the ramp surface, here's the object, and we have the force of gravity is straight down. Well, our y component has to be perpendicular to the surface. And our x component needs to be parallel to the surface, but instead of drawing it here, I'm going to draw it here. So this is FGY, and this is FGX. These are perpendicular to each other by definition. Y and x are perpendicular, FGY, FGX are perpendicular. Also, force of gravity is perpendicular to the ground. Again, basically by definition. Now we define ramps to have the angle from the horizontal, this theta. So using a highlighter or two, here's the first triangle I want to look at. If this is a 90-degree angle, and this is some unknown angle theta, these three angles have to add up to 180. Well, this takes care of 90 of it. So these two have to add up to 90. So this angle here is 90 minus theta. Well then, this angle here between the surface and the y component that I just did in pink, that's a right angle. Again, by definition, we've defined our y direction to be perpendicular to the surface, so it matches up with the normal force. So if this pink is 90 degrees, then this little section between the red and the yellow has to be 90 minus theta, which means it's the same theta. And then notice in this triangle, this is the odd part, that for theta, FGX is far away, FGX is opposite. FGX is opposite, which means the sine function. And FGY is right next to theta. It is adjacent, so it's the cosine function. Because remember, opposite the right angle, FG is our hypotenuse. Hypotenuse. So summarizing those as the equation formulas that in AP1 I just told you, FGX equals mg, x is always cosine except on ramps where it's sine, and FGY is mg, y is always sine except on ramps where it's cosine. So that's how we break those up into components. one more thing to talk about. We're going to send Christian grocery shopping. And so this is the grocery cart. And of course there's force of gravity on it. And Christian, when he pushes the grocery cart, doesn't push horizontally. He pushes down at some angle. So we're going to draw that here. This is the force of Christian. And it's at some angle below the horizontal. Well, then there's a normal force, but before I draw it, Christian's force has two components, an x and a y. So the normal force upward, if it only canceled out the force of gravity, then this cart would move downward because Christian's pushing down on it. So the normal force is actually bigger than gravity in this situation. How much bigger? Well, let's redraw this with components. So F norm, FG, oops, red, F Christian X, and F Christian Y. So our Y's have to cancel, otherwise the shopping cart is floating up in the air or breaking the floor. So the normal force equals FG plus F Christian in the Y direction, only in the Y direction. If Christian was crawling on the floor and pushing upward on the cart, then this component would have been upward, and the normal force would have been less than gravity by that amount. Then this component is what goes into the net force. And we did problems like this previously where there's also friction and figure out the acceleration. But for now, no friction, which is nice. So that's our first shot at applying Newton's laws to more complicated situations.